The fifth lecture on Biot-Savart Law. Initially, I planned to finish the application or discussion on Biot-Savart Law in 4 lectures. But recently, I come across a book, Introduction to Electricity and Magnetism. It is a MIT course lecture. Course notes by S.B. Leo and others, which inspired me to take another lecture on Biot-Savart, on the application of Biot-Savart Law. One point, this is a nice book full of with plenty of animations of very good quality, which will facilitate students to visualize for what is happening in electricity and magnetism. I think it is this book must be consulted by every student. Now let me come to the problem proper. This problem is an application of Biot-Savart Law in 3D. So we are considering a problem, a three-dimensional conductor in the form of a cuboid. We assume that the sides of the cuboids are parallel to the Cartesian axis. The cuboid extends in xy direction. Cuboids extends between plus minus infinity. So in xy direction it extends between plus minus infinity. But on the z direction it is limited to plus d by 2 to minus d by 2. So this is the width. So to say, it is a sheet of thickness d. It is a thick sheet of width d, and a current flows along x direction. So the current density J is a constant, and it is given by I cap J0. Our aim is to find out the field at a point end. Since the sheet extends up to infinity in xy direction, we consider the point to lie. On the z axis. That is the point where field has to be calculated as coordinate 0, 0, z. We consider a volume element dv prime. We consider a volume element dv prime around r prime, so that this is capital R and this is the field coordinate r. Our aim is to find out the field at P. So let me write the thing. First is R, field vector is I cap K, the source coordinate R cap is I cap X prime plus J cap Y prime plus K cap Z prime. So the relative coordinate R is and the magnitude of R is x prime square plus y prime square plus z minus z prime square to the power half. The current density of the dv prime is dx prime, dy prime, dz prime, and current density, it is a constant, so this is I cap J0. So the field at P due to this volume elements, this dv prime is the field at P this is mu 0 upon 4 pi j cross r by r cube dv prime. So if we write the things for this is mu 0 j 0 upon 4 pi r cube is not a constant, still I am keeping it. For this is I cap, this is the direction of j cross so this becomes I cross I is 0, I cross j is k, so this is k cap y prime, and this I cross k is minus j, this is the field. Total field is obtained by integrating it over the cuboid, that is the total field at P is obtained by integrating that is to say, remember that r is not a constant. Oh sorry, I have missed dv prime altogether, so this is dx prime, dy prime, dz prime. So the field is obtained by integrating over dx prime between plus minus infinity, dy prime between plus minus infinity, and this is over between plus minus d. So we take the constant parts out. Mu 0 j 0 upon 4 pi integration dz prime plus infinity. I think it is not, it could not be read properly, so let me write a little bit down. This is z integration for x integration and finally y integration. The numerator will have this thing. We can take minus sign out, so this is k cap y prime plus k cap y prime plus j cap z minus z prime by r cube, that is x prime square y prime square plus z minus z prime square to the power 3 by 2. Let me call it as Iy. So Iy is the integration, Iy is actually this dy prime, oh no, sorry, first thing, there are two parts. One part is involving k cap y prime for which the integrand is odd. So integrand is odd, that is y prime dy prime integrated over r cube. R cube is an even function of y prime. Integrated over symmetric interval is 0. So the first term goes and the field is four pi. The angular part is j cap and this part is z minus z prime dz prime plus and finally dy prime. Let me call it as integration y. So basically integration is Iy is with a square is equal to this part. Y prime is kept and the other part is a square. It is an even integral, so this is equal to 2 times 0 to infinity dy prime a square plus y prime square to the power 3 by 2. If we use the substitution y prime is equal to a tan alpha, then this becomes 2, the limit is 0 to pi by 2, the a sec square alpha d alpha and in the denominator a cube sec cube alpha. So the result is 2 by a square cos alpha d alpha 0 to pi by 2. So this is pi by 2, this is sine alpha, and this is the result is 2 upon a square, that is 2 upon x prime square plus z minus z prime square. So this integration is removed and we write, so we take 2 out, so this makes 2 pi. J0, sorry, Z in and the x integration is now dx prime and in the denominator we have x prime square z minus z prime square from minus infinity to plus infinity. We call it as Ix, x integration. So Ix is firstly it is an even integral, so this is 2 times dx prime x prime square z minus z prime square 0 to infinity. We write it as 2 sec square beta d beta upon where we have used the substitution x prime is equal to z minus z prime tan beta. Now you see that it comes out to be, this is important, mod part, and the integration is d beta from 0 to pi by 2. So result is pi upon z minus z prime. So the field becomes minus j cap, and this pi cancels this, so this becomes mu 0 j 0 upon 2, and the integration is minus d by 2 to plus d by 2. We have z minus z prime in the numerator, mod z minus z prime in denominator, integration over z prime. We call it as minus j cap mu 0 j 0 2 iz. Now the z integration has to be very crucial and has to be calculated very carefully. So iz is, as per our definition, iz is equal to integration from minus d by 2 to plus d by 2 z minus z prime mod z minus z prime dz prime. This is first case. Case A, we assume the point to lie above the set, that is observation point z is greater than plus d by 2. In that case, this is simply iz is simply, you see that this is dz, and the result is plus d. For the other case, this is the case when it is above the sheet, and if we consider a point below the sheet, z is less than minus d by 2. In that case, the integrand is negative. Note carefully the negative sign. So the result is minus d. Because this part is positive and here comes a negative sign. Third, very interesting case. We have never calculated field within the current carrying conductor using Biot-Savart law. We have calculated a field within the conductor using Ampere circuital law, but in none of the previous calculation we have applied Biot-Savart law for the calculation of field within the conductor. The first time we are going to do it. We consider Z to lie between. So Z is somewhere, the observation point is within the sheet. In that case, we write iz as z minus z prime integration is divided into two parts, from minus d by 2 to this, in this case the field is within the sheet, and we have divided the integration from minus d by 2 to d by 2 into two parts. One is minus d by 2 to z, and this. For this part you know that the integrand is plus, because z is greater than z prime, so this gives you minus d by 2 to z dz prime. And for this part z prime is greater than z, so this is a minus sign, and the integration is z to d plus. Here we get z plus d by 2, 2 minus makes it plus, minus d by 2 minus z. The result is 2z. So we see that the integration has three values. This is for one, this is another, and this is the third. So we write the field as field is along z direction. First, this one. So this is D, and the condition is z greater than d plus 2. Then I come to this part. This is twice z when z is in between plus minus d by 2, and this is minus d when z is less than minus d by 2. In the book that I have referred earlier has solved this problem using Ampere-Circuital law, which I am not going to consider here, and I should refer the reader to look at the book. And I have solved the same problem using Biot-Savart law. It would be interesting to have a plot of the graph. You see that there is a negative sign, so the plot, if we plot the field, it is a BP which is along the y direction, and this is the z. This is plus d by 2 and this is minus d by 2. For this part the field is negative, and for this part the field is positive. In between these two parts the field varies linearly. So this is d by 2, this is minus d by 2. This is the variation of the field with the distance. So in the next class we shall be considering magnetic vector potential.